yeah, we're happy to have Eischen, who's here to talk about algebraicity of spin L functions for GSP6.
I'd like to thank Sam for inviting me to speak and also thank the people at IAS who made it possible for me to spend the year here. It's been really great. It's been like my favorite year of my career so far. So I'm glad still to just be maybe just past the midway point for that. So the goal for this talk today is to describe an approach or strategy for proving algebraicity of certain values, in this case, critical values. Of certain automorphic L functions. And then to apply this in the setting of the title. So apply this for the setting of spin L functions for GSP6. And this application to spin L functions for GSP6 is joint work with Giovanni Rosso and Shrenik Shah. So motivation for studying this question in the first place comes from conjectures about, well, not in the room right now, but from Deline and others who spent time here about algebraicity of certain values of L functions. And actually for us, as I'll explain later on, original motivation came from studying P-adic aspects of these, which were also conjectured by, well, tied to the seminar we just had here, Iwasawa's main conjecture and tied to conjectures of Greenberg. But the main tool that we have for doing this, at least at this moment in time, or one of the main tools, is through automorphic methods. So automorphic forms and automorphic representations. For this talk, really, even though the title is about one very specific instance, the thing I really want to highlight is kind of this is a general strategy which shows up over and over again in different guises, and I want to kind of highlight key ingredients, but also be clear about toward the end, about what goes into this case here, because often what happens, I think, especially in, well, at least in the area of math where I work, the area of number theory where I work, is you have a recipe or strategy or program, and it's well laid out, but if you actually want to carry it out in practice, even if you know it really, really well in another setting, you move away like what looks like epsilon away, and suddenly the things you know fall apart and you're lost. And that's actually what happened in this project. We started this project in 2017, and I thought we'd be done by the end of 2017. And it was August or September when we started, which gives you some idea of how confident or naive I was about this. And the reason I was so confident was two things that happened in 2017. One was that Michael Harris, Jianshu Li, Chris Skinner, and I were finishing up a big paper on p-adic L functions for unitary groups that invoked some version of this strategy in a p-adic setting. And the other thing that happened was that well, Shrenik and I were at, and then later Giovanni and I were at a special program at EPFL, and Aaron Pollock presented a result he had constructing a certain construction of spin L functions for GSP6. His goal was to obtain certain analytic properties. He wasn't focused on algebraicity, but I thought that his approach could be adapted to the algebraic setting, as did they. It turned out, as I'll explain toward the end, that it was sure it works out, but it's much harder than we thought. And actually, our goal was to construct p-adic L functions, but it turned out that no one had actually proved algebraicity. So this idea that we were going to p-adically interpolate anything or prove congruences was nonsense, because we just had some numbers that conjecturally were algebraic, but a priori were just a collection of transcendental numbers sitting around them. All right. So for the structure of this talk, I'm going to start with two motivating examples that follow this kind of recipe. They're in some sense simplistic. You don't see all the nuance for later, but they capture what I consider kind of the key ingredients here, and they're explicit. And then that'll lead into our strategy. I'll give you our theorem, and then at the end, I'll say a bit about what goes into the proof. And I'm here all year, so if you want many, many more details than in the hour version, you can come talk to me. All right, so here's our two motivating examples, and we'll scroll later. Okay, great. So the first example, let's consider, we're going to consider the Kummer congruences. So we're going to look at a modification of the zeta function. So I said we're starting with really a simple version. There's no data attached to our L function. It's literally just the Riemann zeta function. For a moment. So we modified it slightly, and the Kummer proved in the middle of the 19th century that zeta p of 1 minus 2k is congruent to zeta p 1 minus 2k prime mod p to the d. Here, just fix your favorite prime numbered p and your favorite positive integer d. Whenever 2k is congruent to 2k prime mod phi of p to the d, and we need one additional condition, which is just that p minus 1 doesn't divide these numbers, or equivalently doesn't divide one of them. It won't divide the other then, since they're congruent mod this number, which is divisible by p minus 1. So he proves this. He exploits some properties. One way you can prove this is using properties of Bernoulli polynomials, which specialize to give you the Bernoulli numbers appearing in the values here. So here, I should have said k is a positive integer, in case that wasn't clear. Of course, there's lots of other L functions out there. You could look at Dirichlet L functions, for instance. In the 1960s, Leopold and Kubota construct packaging these congruences together, P-adic zeta function, and more generally, P-adic Dirichlet L functions. But of course, there's still lots of other stuff that maybe not in the world where Kummer was living, but certainly by this point, there's lots of other stuff out there. And so Serre's idea in the 1970s for how we might recover these congruences and a P-adic zeta function in a way that's actually generalizable, as opposed to, well, I've got these convenient properties of Bernoulli numbers, or Bernoulli polynomials, how far could I push them? But what could be a different approach that extends much further? Well, there are links between modular and automorphic forms and L functions. Maybe somehow we can exploit those links. So his idea, he introduces, if you want to read the full theory, because I'm only going to say a teeny bit of this right now. If you want to read the full theory, it's in volume 3 of the Antwerp series, where Katz also develops his geometric approach to P-adic modular forms. But he introduces P-adic modular forms. I'll tell you what we're going to use about this in a moment. And uses them to recover the Kummer congruences, and more generally, the Capote-Leopold P-adic zeta function, among other things. Say, rough idea, there's many things in there, but rough idea, if you have modular forms with Q expansions, so Fk of Q equals an of K, Q to the n greater than or equal to 0. These are weight K modular forms. with K, I'll just say suitably convergent, p-adically and Archimedeanly, and this is congruent to this guy. So for two different modular forms in this family, you get a congruence. Then the constant terms are also congruent, which out of context does not look like a good deal. Out of context, this is like, hey, you wanted to prove a congruence. Here, instead, let's just check it for A1, A2, A3, A4, A5, and reduce our problem about checking congruence for constant terms to a problem about checking congruences for all the other coefficients. So outside of any context, this looks like a terrible thing to do. But in the context of applying this to the p-stabilized weight 2K Eisenstein series, where this is just this slightly twisted, or this stabilized divisor function. So we've got d to the 2k minus 1, like your usual divisor function, except that we leave out the divisors divisible by p. And then when you get this, he also gets p-adic limits. I just wrote congruences here. It's easy to grasp. And for people who study these things, he's able to obtain things inside of Iwasawa algebras and all the things that you want in Iwasawa theory. And so you recover the Kubota-Leopold p-adic zeta function and the Kummer congruences, because these guys are really easy to study congruences of. This is like, if you want to work mod P, you're basically asking for, you're just asking about Fermat's little theorem in the context that an undergrad would see in a first course in algebra. And more generally, you're asking about Euler's theorem, mod powers of P. And so the question becomes very easy. That's great, and you can extend this to Dedekind zeta functions. And this idea, maybe if you haven't, if you're not that familiar with it, seems kind of weird, but this is builds on an idea of Klingen and Siegel, which in turn built on earlier work of Hecke from much earlier. But shortly before there's a work of Klingen and Siegel proving rationality of zeta values. So for instance, Dedekind zeta values for totally real fields in terms of rationality of higher order, so not the constant term. Of Eisenstein series. So first there's this idea, again, it was already known, 100 years before Kummer, that you've got rationality up to, or you've got rational values there for the values of zeta, but the idea here is to now link things to modular forms so that hopefully you can push things much further. And so we get this, and then we get this p-adic work. This is great, except that all I told you so far is basically the things on this board are just reproving things that we already knew. And if this is a good way to proceed, it should lead to something new. And indeed it does. So shortly after Serre's work, shortly after this came out, Coates and Sinnott constructed p-adic L functions attached to Hecke characters of quadratic real extensions of Q. And then shortly after that, Deligne and Ribbit constructed p-adic L functions attached to Hecke characters of all totally real fields. And then, the next, I guess now you've done all totally real, so you would join a quadratic imaginary, and Katz did that for half of all primes. So this at least led somewhere. those papers start, the first one, that quadratic real case of Coates and Sinnott, is 36 pages. Then Deline and Rivet's paper is 60 pages. And Katz is 99 pages. And they're all published in Inventiones. Like without this context, it sounds like these sound kind of like incremental problems. Like, oh, well, this kind of Dirichlet, like, or this kind of Hecke character. Well, attach that kind of Hecke character. But something's obviously going on since things are actually, as you go along, getting longer. They're still published in a really strong journal. I mean, a lot of what's going on in the background, I guess there's two things. One of them is geometry. So, for instance, Deline and Rivet's paper relies on Michael Rappaport's thesis, which was being written at that time, and developing Q expansions for Hilbert modular forms. And then there's also a lot that goes into constructing the Eisenstein series. So two hard things going in the background are geometry and this Eisenstein series here. I like it because it's explicit. You can see congruences easily, but it's misleading because usually you can't just open up a book and find things like that. So I want to go to our second example, which brings in another ingredient that's going to be important here. So let's consider the Rankin-Selberg convolution. D of SFG, and Bn over n to the s and greater than or equal to 1 here, where lost part of the board. F of Q and G of Q are modular forms. This is a F's a cusp form. G is a modular form. This guy we also will take to be primitive, so it's eigenform appropriately normalized, and scale of weight K bigger than the weight of G, which is L. And it turns out that for appropriate values of S, when you normalize by the automorphic period, you get something in Q adjoin the Fourier coefficients of F and G. So you're just adjoining the A and, oh, didn't tell you what these are. A and Q to the N. This guy has Fourier coefficients Bn. Q to the N. So you're just adjoining all the ANs and all the BNs using the standard notation here. For, I obviously have to put a condition on S. Here it's an integer such that K plus L minus 2 over 2 is less than S, less than K. And the key, and this is due to, this is a theorem of Shimura. From the mid 70s, maybe 76-ish. The key ingredient or key maybe observation, which actually in some sense goes back to Rankin, is that this convolution here can be written as a Peterson pairing of a certain tweak of F, basically taking some complex conjugation into account, paired against an Eisenstein series we take this Peterson pairing here of these Eisenstein, their forms is an Eisenstein series here. Generally, you have to avoid from non-holomorphic ones, but they can be realized from holomorphic ones by applying certain differential operators, which raise the weight by 2r here. So if you go through the mechanics, both sides of this then have weight K. And the point is that this guy here is basically to decompose as something times F plus something orthogonal when you decompose your space of modular forms in terms of simultaneous Hecke eigenforms. And so when you pull this out, you get this C, which gets tied to the L function and lies in your desired ring, and you get to move along happily. Okay, this then was later, like about a decade later. Hita in the mid-80s builds on this idea to construct P-adic Rankin-Selberg convolutions. And so now we've also now got at least attached to something other than characters, attached to modular forms, some algebraicity results or rationality results, and P-adic results. And I guess the takeaway principle before we go on is basically that properties, so involving algebraicity or congruences or P-adic interpolation of Fourier coefficients and pairings, especially Peterson pairings, of modular forms, especially Eisenstein series, imply, at least in this is a principle in favorable cases, at least corresponding properties for associated L functions, or at least certain values of those L functions, at least in favorable conditions. So this suggests that maybe there's like a three-step strategy, or I don't know how you want to count it. I usually go through 3 steps, and the very broad strategy is to take so realize your L function as a pairing. These are really hard steps though, and different flavors from each other, which is how they became different steps. Find a suitable, whatever that should mean here, so something with its Fourier coefficients, family of Eisenstein series, and prove my Eisenstein series is black or bold. Prove E. And pairings with E have desired rationality or algebraicity or P-adic properties. I'll just say algebraicity to encompass everything here. This kind of summarizes what happens over and over and over again in many different cases, but these are really hard. And just because you have a pairing, you still might not be able to get anything algebraic out of it, because lots of these integral representations, like I mentioned, Aaron developed it for analytic reasons. That's often what the motivation is for people in this industry. Constructing these Eisenstein series, also in general, really hard. Not that Sarah example is nice because you can see everything explicitly, what's going on, so there's nothing abstract or hand wavy there, but in general, you can't just like open a textbook and read off what you want. So I want to just talk about a few cases where this has been carried out, leading up then to my theorem with Giovanni, Rosso, and Shah. And I should note there are some other approaches as well. I'm highlighting ones here that are gonna like kind of be analogous to the tools we use in our paper to highlight some ideas. But for instance, I mentioned this result of Deli and Rappaport. Kazunogis also had a construction of P-adic L functions using adapting a method of Shintani. There are other things out there. I'm highlighting these because I want to get to a particular place. So this strategy, did I call it a strategy or recipe? Strategy, great. So this strategy, this 3-step strategy has been carried out in various places for I'm highlighting results again closest to this. So L of S pi chi standard Langlands L functions with pi acuspidal automorphic representation of a unitary group of whatever signature you want. Also for this thing here of a symplectic group, so using Siegel modular forms, and in the algebraicity algebraicity here was proved by mostly Harris, but also some other people extending this approach. So yeah, this on the other side just to highlight. So the algebraicity results are mostly due from the early 80s to Harris, also some work of Shimura, and then Harris had some students later who filled in some pieces. Symplectic groups, Harris, again, Shimura, also Shimura's student, Storm. Again, this is in the early 80s. And then the P-adic construction, at least when this is ordinary, so an ordinary condition, and with a similar condition on P to the one that Katz has for P-adic L functions for CM field, this is constructed in work of myself and Michael Harris and Jen-Chu Lee and Chris Skinner from 2020, and that same year, work of Zhang Liu. There's a lot of Liu's out there. So Zhang Liu constructed P-adic L functions in the case of symplectic groups. She did this in full generality earlier in the 90s. Becher and Schmidt had handled the scalar weight. The scalar weight case. So we've got some results for standard L functions here. So then you could ask naturally, there's another thing when you move from unitary to symplectic groups. There's another thing you can ask about. Actually, before I even get to that, I want to make a remark about this. Like I was mentioning lengths of papers, like this paper is now 160 pages long and relies a lot on two of my earlier papers constructing the Eisenstein measures that we need. So things are definitely getting, at least if the amount of space it takes to explain something is any indication, have not reached a point where they're somehow collapsed down, which might be what you would hope would happen with lots of examples out there, but that's not the state where the field currently is. So natural question now is, what about spin L functions? So we're talking about symplectic groups. The dual group, the spin group, so we're looking at GSP2G, so you can ask then the dual groups, GSP2G plus 1. And so you might as well ask in that setting, what about this? For pi acuspidal automorphic representation of GSP2G. And this is a lot more underdeveloped, I'll say, a lot less developed than the situation on this board. So you can ask about algebraicity and P-adic things. You may have noticed there's often a lag between the result for algebraicity and the construction of a corresponding P-adic L function. So if you start G equals 1, this is just a shift of the L function of a modular form. It's heavily studied. Shimura, also Manin, in the 70s proved algebraicity. P-adic There's lots of P-adic papers about this, or papers of P-adic aspects of this. So Maser, Tate, Teitelbaum in the 80s did a lot with this. So now if you go to 2, Harris, same Michael Harris does all those results over there, in 04 in a paper who I never remember the title, but it has the word occult in it. So you can probably find it without actually any mathematical, just remember the word occult is your keyword, without knowing what mathematically anything else about what's in there. He proved algebraicity in certain cases by building on an integral representation of Novogorsky. And then in 21-ish, David Loeffler and Vincent Piloni and Chris Skinner and Sarah Zerbis constructed a P-adic L function whose values interpolate these guys. You can ask about 3, that's this talk, so that's what I'm gonna tell you about in a minute. This is, I should say, in progress, work in progress, not paper in progress. And then you can ask about greater than or equal to 3, and there's just a bunch of question marks here. I don't know how many people there are in this audience, but probably some who are familiar with integral representations beyond the GSP6 case. So maybe you have some kind of alarm bells off where you're like, why question marks? So there are integral representations, this step 1 from over here for GSP2G for a few larger Gs, like due to Bump and Ginsburg, but I don't think anybody knows how to make any algebraic sense out of them. That's why there's just a bunch of question marks going across here. So let me tell you what this theorem of myself and Giovanni Rosso and Shrenik Shah says. So let pi be a cuspidal automorphic representation of GSP6 associated to a polymorphic Ziegel cusp form, so an eigenform P of weight 2r greater than or equal to 12. Then L of S pi spin over 4s minus 6r minus 6 times phi paired against a slight tweak of phi, basically complex conjugation of the Fourier coefficients. If your coefficients are in the real numbers, you can just put phi here. This is in Q. Adjoin the Fourier coefficients of phi. Before I go on, I just want to tell you about what goes into this result here. I want to make.
Where's S?
Oh, whoops! Thank you. Yeah, no, for all. Yeah, no. So we have. Thanks. That's like I felt like it looked kind of short, but so S is an integer from ranging from 4 to r minus 2. Since you just asked about S, I'll say a little bit more about this. These are the S values where this works. This L function centered at a half. So you'll notice if we're looking in the right-hand side of the critical strip, we're missing 1, 2, and 3, and we haven't gone to the left. 1, 2, and 3, my understanding from talking to, mostly to Gordon Savin is that well, it might be possible to do something there. You might expect a pole for maybe for reasons you know, I don't, or somebody in this room knows, but you might expect a pole there. Our proof is such that the way we prove things, we only can do these values. But there's some reason to expect that we might not be able, just as in for a general phi, to be able to get 1, 2, 3 anyway. So aside from, there's the reality of what we know how to do, and there's also some mathematical reasons that you might not expect is just without some more conditions to get those other 3 points. This scalar here, there's a few things here. We're working over, I guess we're working over Q. I think this could extend in a straightforward way, just with more tedious bookkeeping, to other totally real fields. And when Aaron was here 2 weeks ago, I talked to him and he said he'd actually worked out, like Wietek-Gen and Gordon 7 for some reason needed this over other totally real fields, and he worked that out and it went through straightforward as expected. You might wonder why we're working with only scalar weights here when, unlike in that modular forms case, there are other weights here. I also expect that this can be worked out for vector weights. Aaron only, in his paper that I'll get to in a moment when I describe ingredients, we use a result of his, which was only worked out for scalar weights. And I like working out the vector weights. I think I know exactly what to do all the way through, but takes, it goes in a different direction from what we're doing in this paper. So let me tell you, we can get rid of this. Before I go on to talking about what goes into the proof, and I have told.
440.
Oh, great. Okay. I feel like I must have skipped something, but great. So before I get into key ingredients in the proof, are there questions about what I'm trying to prove? Okay, great. So great. So in the key ingredients in this proof, the first thing that goes in is an integral representation of error. And this is the thing I keep saying. The reason that we have scalar weight, or the reason it's over Q, is because of that. So he looks at this completed L function. This thing here is, so gamma factors times our desired L value. I should say he also only looks at the level 1 case. We extend it to higher levels. You write this as an integral over GSP6 of the delta, pretty innocuous looking integral. Z is the center here. I should say 0, but del's just so it doesn't go. Phi of G, so phi is the same phi from the theorem. E 2r of GS dg, this is a weight 2r Eisenstein series. So far it looks pretty innocuous. I mean, this thing right here is a pairing of phi against this Peterson pairing. So it looks like, okay, we're like back in the same.
Eisenstein series on what? Where?
Yeah, that's the next thing I'm going to tell you. So that's my thank you for prompting. My next line, yeah, so that's what's going to make things trickier. So E, I'm just going to call this guy E, so I don't have to keep. I'll attach R and S if we need them. But for now, E is just stands for this kind of Eisenstein series. Is an Eisenstein series. It's a Siegel Eisenstein series, so that sounds nice. But on a group G, which contains GSP6, this group, I'm going to tell you some properties of it, and if you want the full definition, you can ask me after my talk, but it's going to, well, maybe I'll have time at the end because I seem to be moving kind of fast, but I'm not going to, I'm going to give you a bunch of qualitative properties so you have some sense of what it is without writing out every detail, and you can ask me at the end, and I'll spend 5 minutes showing you at the board or any other day in the next 5 months. So it's an Eisenstein series on here, so here's a bit about G. G acts on a 32-dimensional vector space over a field F of characteristic 0, whatever field you want. You can start with Q and then go to whatever character, or go to R, or whatever field you want to use. The vector space is F plus H3 of B. I'll tell you what B is in a moment. Plus H3 of B plus F, where B is a definite, so ramified at infinity, quaternion algebra over F, and G is defined to be the similitude group in
What is H3B?
oh yeah, I meant to tell you that. Thank you for asking. This is H3 is 3x3 Hermitian matrices. So here the conjugation's the usual one, the involution's the usual one on the quaternions. So we've got this. Now G is defined to be this, a similitude group in here. Observing, I'm not going to write down in the, this is where I'm not going to write definition, but you can ask me after you want. A particular, it's a specific symplectic form up to similitude, and a specific quartic form up to similitude. I'm going to tell you a little more about this group.
Is it a type E6 or something? Or?
That was actually, so you're asking really good questions because you're all always asking, because I keep asking the next thing I'm going to say. So I shouldn't tell you that. So it just, but I guess it's set up very well to leave like what I'm saying, because you're asking exactly what I want to tell you about next. So yeah, so it's a half spin group of type D6.
E6.
So it's a quotient of spin 12 or G spin 12 by not the thing that goes to the orthogonal group. It goes so the center has two Z mod 2Z actions, and it goes to something else that I don't think has a name. So it's classical. It's a classical group, but it feels, you mentioned E6 or something?
Yeah.
It feels like an exceptional group. Maybe I won't write that. That's not really it. So maybe I'll go on and tell you what feels like an exceptional group means to me in a moment. I'll just tell you what this acts on, because it acts on something that's kind of like familiar-ish looking to me. So G acts on a Hermitian symmetric space consisting of all x plus iy in H3 of B tensor C, such that y is positive definite. So sign means positive definite. Here I mean x, and let's say we're over R now. X and y are in H3 of BR, and then I've got the I. So typical things. So like if you replace B here with C, with C, then you're looking at the Hermitian symmetric space for unitary groups, the PEL problem, which I'm used to. On the other hand, if you go to octonions here, I think you're in your exceptional case, but I'm speaking, I think so. Anyway, so you got this thing, how does it act here? Because this like doesn't look like it matches up. So there's a map, which you can ask about later if for some reason you care, but just to convince you there is something, there's some map from R from H to W, and the action and the automorphy factor are defined simultaneously by J of GZ, R of GZ. So there's some action. It's like annoying to work with. Don't think of working with unitary groups or something. It'll just send you on a the wrong path for as long as you keep doing it. Even though I said that, I will say there is another group. This is like the last. Oh, this is like the end of like mini golf where you deposit the ball. Well, so there's another group, G tilde. I'm only telling you this because I'm giving a talk and I want you to have some sense of the shape of this group. There exists another group, G tilde, that's a double cover of G, and also of GU33 of the quaternions. I spent a lot of time during the pandemic at home trying to prove local properties by like going somehow through this because I thought like it looks like a good idea because I like unitary groups, and I never got, the only thing that did was cost me a lot of time. I've never proved anything through going through here. And well, I was like having an email conversation with Kaiwen Len the other day about something I'll get to in a moment. And I felt kind of reassured because at least in some related contexts, he told me it would be like really difficult to do this sorts of things, like various things by going up through here, which I'd given up on several years ago. But it seems like sometimes I give a talk, and if there's like a large enough seminar and enough knowledgeable people like here, inevitably someone comes up afterwards and tells me how like they have their 15-minute approach. I don't think there's like a 15-minute alternative to doing work here.
So sorry, what is,
Yeah.
this is a group over Q?
Yes.
What is the field F that you,
Oh, F was just some characteristic zero that you can start over Q if you, I'm just saying it acts on this vector space. If you wanted to start over Q, you can. You can even define this as an algebraic group over Z.
Positive,
What?
like, it's totally real, right? Otherwise, how do you define positive?
Where?
I guess.
This is over R.
Yeah, G of R, excellent.
Where did I? Oh, yeah, I want R. Sorry. Here, I'll start over Q. And
okay, so then,
just replace it. You can tensor up to whatever you want from there.
and which definite quaternion algebra do I take? Or
You can take whatever one you want. I don't think you need to.
I see, okay.
What does GSP6x on W?
Oh yeah, so there is a I'm not going to write it on the board in this talk, but it's involved. But you can take the defining space for GSP6. So you have that vector space, which is much smaller than here, and it's possible to embed that in a way so that you can realize GSP6 realize that space inside of here, and so you can realize GSP6 inside of G, and correspondingly realize the other part of your question should be like what's going on over here, and you can realize the Siegel upper half space for that inside of here. So it is possible to come up with realize the defining space in a natural way here, so that you get GSP6 inside of G. I want to say something about H. So actually, I now feel like in 3 days I'll have, so it's not clear to me currently, but I'll just say a few words about this, and then in the last 10 minutes I'll talk about something else. But H has well, maybe I'll just say something even stronger, is it's not even clear it's a abelian type. There's certainly no TEL moduli problem sitting there for you to like exploit. In many ways, this space feels like the forms, like everything that's going, the group feels exceptional in the sense. So what do I mean by that? I'll say something about where we study the Eisenstein series. So for the Eisenstein series, we have this E. We break it apart into, because we're proving algebraicity and not p-adic properties, it turns out, unlike my life in the p-adic world, we have to also consider pieces with singular, with Fourier coefficients indexed by singular matrices, where this guy is J has non-zero Fourier coefficients only at the Fourier coefficients are indexed by Hermitian matrices of those quaternion algebra at beta of, so there's a notion of rank here, which I won't get into, but generalizes your usual notion of rank. J, and to understand these pieces, as is the case, like typically when you're computing a Fourier coefficient of an Fourier expansion of Eisenstein series or modular form, you don't just write down the definition and like compute from scratch. You usually like build on existing body of knowledge, and the places that turned out to be useful, aside from a little bit from Shimura, which I've used in the unitary setting, were all papers on exceptional means and modular forms on exceptional groups. And
E is holomorphic, is that right?
E is holomorphic, or sorry, yeah, oh, no, let me, I will, in my about E, I will, so E is, E starts out holomorphic, but then we apply a differential operator, and so it does not have to be holomorphic all the time. So E to R of GS, there's a Mashimura type operator that you can apply. It raises the weight by 2. I'm not writing down the precise definition here, but the way we have it normalized is that E to R of GS converges absolutely for S greater than 5, and is in our particular normalization holomorphic for S equals R. And these like the terms look like with whatever like J is over there, taking some norm of J and raising to the R minus S or something. Like when I say we get a holomorphic for this value, like think about your usual, any familiar case of Eisenstein series, like in modular forms or whatever, how you set it equal. So it's just our normalization. So this actually comes into play. You asked about well, I hadn't written down what S was, so you prompted me to write S here. These conditions are precisely what determine the values of S for which we're able to work. These conditions combined with, where is Aaron? I wrote down a pairing of Aaron. Did it disappear? Well, we had a pairing of Aaron on the board, which apparently went away, which looked like, so we had this S minus 2 pi spin equals this integral of phi E that I wrote down before. And this shift by 2 and these conditions here combined with the usual approach to algebraicity, which shows up in that second motivating example, are precisely what give you those S values there. So G is nearly holomorphic at least. What did that answer? I don't know exactly what you wanted to know about it. Okay, so the Eisenstein series that we end up working with has a nice Fourier coefficients, and nice, meaning we get rationality results, which we need in order to get our our result of the L functions there, and furthermore, nice interpolation properties. So we have these nice Fourier coefficients, and so it's built heavily on, or employs heavily, rather, work of Martin Harl and Tsao and Henry Kim for modular forms in various exceptional settings. When I say we get nice Fourier coefficients, we actually get something nicer than you might expect from what I have on the board right now. So far, I've given you a result about algebraicity, a very clean result about algebraicity. If your coefficients of your cusp form are algebraic, then you get something algebraic out. If they're in a CM field, you get a CM field out, and so on. But actually, I mentioned at the beginning, we want to, well, our original goal was P-adic things. There was no theorem like this sitting there, so we had to do something. We wanted to do P-adic interpolation, and one of the things you need there for that is a P-adic family of Eisenstein series, and we wanted to interpolate a character. And so actually, our Eisenstein series, you can work, we have ones that work for this, clearly, because we have theorem there, so it works, but also incorporate a twist by a Dirichlet character. And the goal there was basically to be able to vary this character. The goal still is to vary the character p-adically. There's a few things that are challenging. One, which I think we've completely surmounted, was what to do with this group H by basically reducing all our problems after we've computed the Eisenstein series down to stuff about GSP6, where every life is very nice. Another issue that arises is this integral representation that Aaron produces a non-unique model. And so that makes things a little harder with computing Euler factors. And so if you're computing a p-adic L function, you don't just want p-adic limits, but you want to know about the Euler factor at P. And that turns out to, I mean, I have some ideas, but it turns out to be harder. And it's very different from this doubling setting. And then the third thing is, at the moment, we have a twist, but only in certain, in our L function, only in certain cases. If you were to just read the Eisenstein series part, which is the bulk of the paper, most of the papers are Eisenstein series, you would think we're completely in business to have p-adic L functions immediately, or at least, and we can get like a p-adic, if we restrict this function to GSP6, we have a p-adic measure, p-adic family of Eisenstein series pretty easily. But like I said, Aaron only worked in level 1. We extended the level here, but there's something, I talked to Aaron 2 weeks ago, but just haven't implemented the suggestion he gave me, which sounds plausible. At the moment when we extended things, we couldn't quite show that our integral remained, this integral here was still was well defined, and so there's so I'm being careful here. But maybe if I gave the same talk in like a few months, there would be a twist there. So I am going to, I want to just say, since I have a minute, I want to just wrap up by saying something about relationship with, so when I drew that little chart, there weren't a lot of other algebraicity or p-adic interpolation results for spin L functions, but even of that small amount there, it feels kind of ad hoc, which you might have also gotten that sense, because I was like, what about 1? What about 2? What about 3? But these aren't even really generalizations of each other. Like in this paper, Chris's paper with David and Sarah and Vincent, they're working with non-holomorphic, that's correct, yes? With non-holomorphic forms, we're working with holomorphic forms. Their weights are of a slightly different nature from at least I believe, from our weights, from my looking at it. For GSP6, there's also recent work of various people, Francesco Lemma and Antonio Cauchi and Joaquin Jacinto, Rodriguez Jacinto, working more on the algebraic side, and they're working with non-critical values. We're working with critical values. Hopefully someday all these things fit together, but at the moment, like these things are even more ad hoc, I think, than maybe they shouldn't be. But the state of the art is that things in this setting are even more ad hoc than maybe you would get the sense just looking. Like whatever patterns your eyes are making of like things being generalizations, that's probably overly nice. So I'll stop there, and if you have questions, you can ask me now or dinner or for the next 5 months. Thanks.
Any questions for Alan?
What do you mean by nice Fourier coefficients?
Oh yeah, so they look like polynomials in beta. So there's no determinant in this setting because we're working with quaternions, but it's a norm, which you should think of as the analog of determinant. And so there's something like normally, like when you're working with modular forms, you've got like this det beta to the k minus 1 or an n to the k minus 1 or something. And then if you're twisting, you've got some chi of n. So like if you were working with like you might see coefficients that look something like this in a like Eisenstein series in the modular form setting. For us, we've got some polynomials in we usually would have polynomials in this appearing. Here, let me say a few more words so this is clearer. So this is a modular form setting. In the analog of that here is we've got some polynomials in chi of n of beta to appropriate, I don't remember what our powers here are, but some appropriate power. This, and I write norm here, think determinant, but because these are quaternions, determinant is not literally a determinant. This is a, like in between here, like in, when I'm working with unitary groups, like for instance, is constructing Eisenstein measures for that, you have polynomials in analogous kinds of things like that. So that's what I mean by nice. Is that what you had in mind though?
Yes, but is this for all Fourier coefficients or only the one that corresponds to E3?
Oh, sorry. Yeah. Oh, good. Yeah. So these are the E3 ones. The other ones, there's some annoying calculus that goes on. So you've got a bunch, you have some other norms, which look like, yeah, thank you. And naught is just constant term and pretty simple. But for these guys, you've got some other norms, which are basically like you're renormalizing things and then taking like 2 by 2 blocks from the top of something, or just the upper piece, and you have a whole bunch of pieces like that. So yeah, this is only this, otherwise you would have like zeros. So if, yeah.
You never get L functions?
What?
You never get special values of L functions?
What do you mean we never get special values of L functions? 'Cause that's,
I mean, for example, if you start with Eisenstein series for SL2, the constant term is a value of an L.
oh, do we get an L function? We have some Dirichlet L functions that we're normalizing by, but I don't see, I guess somewhere in there probably hidden. I mean, what you're pairing, I mean, but no, if I look at the Eisenstein series on this big group before pulling back and pairing, I don't see that in there. But we do have some Dirichlet L, some products. There's products of Dirichlet L functions, and what precise product is appearing, like how many terms there are, depends on whether it's you're in the 1, 2, or 3. Like in the 3 piece, there's only 1, and then there's 2, and then 3, or vice versa. So there's some Dirichlet L functions, but I don't see the anything else.
These are the Fourier coefficients on G that you've told us, right?
Yeah.
Did these determine in a simple way the Fourier coefficients on GS P6?
Yes, so that's key, in fact, because there was a period where I was just like, well, don't know the answer to, no moduli problem, like, don't know what's going on over here, no Q expansion. They look really nice, but I don't have a Q expansion principle, or like, these are calling out to be interpolated, but there's no p-adic Q expansion, no p-adic anything, no Q expansion principle, not enough structure to do anything. And it's like, well, that was unfortunate, a big time sink, but it turns out that they do, using the structure of how GSP6 includes into G, you restrict it and you still get linear combinations of these guys. And that's really key because that's what saves you and lets you continue on with the program and have a Q expansion principle and everything.
Just finite linear combinations.
Yes, yeah.
You have to make any choices for the data and that builds the Eisenstein series for that, or is it just?
No. No, but that's a really good point. You don't always get to talk in a talk, right, about the thing where you were stuck for a long time, and then you give a talk and you like talk about everything that works. But there was like a long time where I'd say like things I stuck on were just this group G. I tried really hard to pretend I was dealing with like this G33, and I often, if I'm working with people, I'm like, okay, I'll take the Mastamura operator because they always deal with the differential operators. And I was like, this will take me, I don't know, like I'll get back to you in 2 weeks or something. And it was like a long time until I just pretended I didn't know anything and went to G. And then the other place we really stuck was this, not understanding the structure. But once we were like, oh, we can restrict to GSP. So you have to work on G to get the Eisenstein series. You have to do all the Eisenstein series stuff up there. But then to do the algebraicity stuff, you then get to restrict it. Are there questions, concerns, comments? If there's someone who's really good with Shimura varieties, like, as I have a very clear idea, I will otherwise in the next few days probably work this out, but like I have a sense that if there's somebody who's really good with this sort of stuff with like the subtleties for type D, I would appreciate if you would come up and ask me about it after the talk. You won't affect anything about this project, but it will just relieve some confusion possibly.
Any more questions for Ellen? Oh, let's thank her again.